Hello and welcome to our next lecture. This time I will talk about classification. So I will explain an example of classification problem and what is the basic algorithm that we can implement to solve this kind of problem. This algorithm is called logistic regression algorithm. And then I will explain a bit two other methods that we can implement. One is the perceptron, and the other is the Newton method. Okay, so imagine that you want to program a software for detecting spam email. So here we have two examples of emails. The one up here is spam, and the other down here is standard or normal spam, non-spam email. So for this example, imagine that we are going to represent each email as a vector of only two variables. Let's say that we are going to check if our text has the word invited, for example. If it contains the word invited, we are going to give the first variable the value 1. If the email does not contain that word, like here we don't have that word invited, we are considered the first variable to be 0. So 0 or 1 if we don't have the word invited, or if we have it. And the second variable will consider the word opportunity. So if our text contains the word opportunity, we are going to have a 1 for the second variable, and if not, we are going to have a 0 for that second variable. So this is just a very simple example of how we can codify the text of our emails. So when we see the input vector, just think of this small vector that will represent our email. Now, the classification is the same as regression, let's say. The only difference is the output. Do you remember that we said the difference between regression and classification is the output variable? In the case of regression, we can have any real number as an output, but in the case of classification, we can have only a finite number of discrete values as an output. In the case of binary classification, we can have only two possibilities. In this case, we are going to use 0, 0, and 1, but these are simply labels. So there are other algorithms that we are going to study that instead of 0 and 1, they need to use -1 and +1. But in this case, it's going to be 0 and 1. So in a binary classification problem, we have positive examples. We are going to call positive examples when the label equals 1. In this case, we are going to refer to spam email. And negative examples when y equals 0. In this case, it's going to be no spam email. And as we said before, the x, which is the input vector, may be some features of some piece of email. In our case, we said that maybe it could be if the text contains the word invited, and if the text contains the word what was the word opportunity. Okay, so this for this example, our x is going to be those two variables where we have these two words. Okay, so we could approach the classification problem ignoring the fact that y is a discrete value and use linear regression to try to predict y given x. So you could say, okay, I have implemented already my linear regression algorithm. This algorithm can approximate any real number as an output. And in this case of binary classification, we are saying that our outputs are going to be 0 and 1. And you can say, okay, 0 and 1 are also real numbers. Why we cannot use the linear regression, the same algorithm for linear regression, to solve this? And the answer is that you can do that, of course, because 0 and 1 are also real numbers. But that is a very bad decision, because the result is going to be suboptimal. It is very easy to get problems in which doing that as a solution will give you suboptimal performance of your algorithm. So there's a better way to approach this problem. Intuitively, it does not make sense for our hypothesis H to take values larger than 1 or smaller than 0, because we can have only labels like spam to be 1 or non-spam to be 0. So the only possibilities that we can have are 0 and 1. So it doesn't make sense to have our H to be to output any number. So to fix this, we can evaluate our hypothesis. Remember that our hypothesis here that we're considering is, for example, a polynomial, and that could be expressed as the dot product of the vector of parameters theta and the vector of input variables. So the idea is that this H, we can evaluate it in another function that I am calling here G function, and this function could be the logistic function or sigmoidal function. This function outputs only numbers between 0 and 1. This is an open interval in the left and the right. So this function is one of many that we can use, but this function is very popular and it is used a lot because it has two main properties. One of these properties is the one that we need, that it can bound the output between 0 and 1, and the other is that the derivative of this function is very simple to compute, and we need to compute the derivative of this function. So this function looks like this. It's like an S-shaped function, and as you can see here, you can evaluate any real number. So z can go from negative infinite to positive infinite, and the output will only go from 0 to 1. And since this is an open interval in the left and open interval in the right, we will never get an exact 0 or an exact 1 as an output. So we are going to get very close to 1 if we go to the right, and we are going to get very close to 0 if we go to the left. Okay, so this is one of the properties of this function, that it is useful for our binary classification problem. The other one, as I said, is that this function can be you can compute the derivative of this very easily. So here I'm going to leave you the steps, step by step, of this derivation of the function, and the only trick that we can use here is this part here, when we simply add a positive 1 and a negative 1, so we are not affecting the numerator. But by doing this trick, then we can separate this fraction here as one containing the positive 1 and the exponential here, and other with a subtraction containing only the numerator 1, and this divided by this will become a 1, here, and this is exactly the logistic function. So when you compute the derivative of this function, the derivatives is written in terms of the same function. So we will get g of z times 1 minus g of z, and this derivative is going to be useful when we derive the algorithm. So now let's see a way to derive our logistic regression algorithm. Let's take a probabilistic approach to do this. So let's assume that the probability that the label or the output y equals 1, given some input vector x with parameters theta, equals the evaluation of our function h of x. And suppose that the other possibility that we have y equals 0, the probability of having y equals 0 given our input vector x is going to be 1 minus the evaluation of our function. Okay, and this is okay because we have only two possibilities, 0 or 1. If the probability of being 1 is x, then the probability of y equals 0 is 1 minus h. Now we can write this more compactly in this way, like the probability of y given x with parameters theta is this product here, where you can see here that in the first factor we have h to the power of y, and the second factor we have 1 minus h to the factor of 1 minus y. So remember that y could be only 0 and 1. In the case where y equals 0, this will be 0, and then the first factor, h to the 0, will become 1, and mainly we are ignoring this factor. We are transforming this into 1. And if, as we said, y equals 0, 1 minus 0 is going to be 1, and then we are going to consider this expression here, 1 minus h, which is exactly this case here, and this is when y equals 0. And if we say that y equals 1, then this is 1, and this is going to be 1 minus 1, 0, and then we are going to ignore the second factor, and we are going to keep only the h, which is this case here. So this is simply a more compact way to represent in only one equation these two equations here. Okay, now we would want to maximize the likelihood given the training data that we have available. Assume that we have m examples of emails. Some of these emails could be spam and some would be non-spam. We can write them the likelihood of this data. So the likelihood, this big L, remember, is a function of the parameters of our probability distribution that is going to explain our data. So here we have the likelihood having as an argument the vector of parameters. This is going to be equal to the probability of y given our set of examples, and that we have a vector of parameters theta. So this probability, assuming that each of the examples were generated independently from each other, we can write it as the product for every example in our data set, from example 1 to example m, as the product of each of these probabilities. The probability that, for example, example 1 is going to have a label y given the input vector for that example 1, or for example 2 the label of example 2 given the input of example 2, and so on. Now we said also that this probability could be expressed like this in the previous slide, and this definition of the likelihood, we wanted to maximize it, but remember that here we have too many products, and that is going to be complicated for the computation of the derivative. So instead of maximizing the likelihood, we're going to maximize the logarithm of that likelihood. So we introduce the log function, and when we apply the logarithms to this expression above, this power here becomes a coefficient here, a factor, and the same with this one. It goes down here, and instead of products, now we are going to have a sum, and this is very easy to derive. So we are going to, in this case, to maximize the likelihood, so we can use gradient ascent, and that means that each of the parameters will be updated with the current value for that parameter, plus, this plus is because we are going to go up, is gradient ascent, plus some small portion of the gradient of the log likelihood. Okay, so remember that alpha is always a value between 0 and 1. Now this is the gradient, but we need to compute a numerical way so we can program this. So we will need to compute the derivative of this log likelihood expression with respect of each of the parameters of our model. So we need to compute the partials with respect of each of the parameters. So computing this is also very simple, because we have a sum. In this case, we are going to consider the derivative only for one example, but it's the same with the m examples that we have. So in this part of the derivative, you see that you need to compute the partials with respect of some parameter j, and the function here g is our sigmoid function, this S-shaped function. But as you remember, the derivative of this was in terms of the same function g. So here we have g of the dot product of theta and x times 1 minus the same function. Okay, and finally we need to compute the derivatives, or the partial derivatives, of the dot product with respect of theta j. So if in this part, if you remember, since only one of these terms will contain j, all of the remaining terms that don't contain j will simply become 0. So in the end, we have only here the x that is multiplying the parameter theta j that we are updating. And then here, just simply rearranging the order here, we get to this expression. And if you remember, this is exactly the same expression that we got when we were working with linear regression. So given that the partial of the log likelihood is this expression, our least mean square update rule for classification in this case can be written like this. Okay, where this h now involves also the evaluation of the g function, of the sigmoid function, which is this S-shaped function. And now you should consider that this function is non-linear, and therefore, even though our learning rule is or looks like the same, it is not the same, because now this h is a non-linear function. In our case of linear regression, the h was simply the dot product, and that was a a linear function. In this case, this new h for classification is using this sigmoid function, and this is a non-linear function. So we end up with the same update rule for a different algorithm and learning problem. So if we look at the algorithms looks basically the same, but now here we have a g instead of h, just to remind you that after computing the dot product, you need to evaluate that dot product in the logistic or the sigmoid function. So this product here would represent, for example, a polynomial. After evaluating the polynomial, the number that you will get with the evaluation of the polynomial, you need to evaluate that number in the sigmoid function, and then you will get a number between 0 and 1. So in the same way that we studied this for linear regression, where we had the option of batch gradient descent and stochastic gradient descent, here we have exactly the same. And usually the most popular way to implement this is using a mini batch gradient descent, in which we can define how many examples we need to consider in these products here and this sum before we update each of the parameters, which is usually again between 10 or 1000 examples. Okay, so how can we compare two different models of classification? Well, of course, the first thing we can compare is the error function. So we can plot also, like in the same of linear regression, how the loss is going down, how the error of the prediction is going down. But another way to compare models is considering how good our model is for detecting true positive examples or false positive examples, or a combination of both. So first, let's check the meaning of this. So a true positive, we call an example a true positive when a positive example is correctly identified as positive. So in our example, whenever an spam email is classified by our model as a spam email, that is a true positive, because it is an example that was correctly identified as positive. In the case of false positive, this is a negative example incorrectly identified as positive. So this would be the case of a non-spam email that was classified as spam. So it is being classified as positive, but this is a false positive, because in reality it is a negative example. It is a non-spam. A true negative is a negative example correctly identified as negative. Like we have a non-spam email and it is classified as non-spam. And finally, a false negative is a positive example incorrectly identified as negative. So this is the case when we have an spam and it is classified as non-spam. Okay, considering these numbers, we can define the precision as a concept that will answer the question how many of the examples identified as positives are indeed positives. So with this precision measure, we are answering how many of the examples identified as spam are indeed spam emails. And you compute this number by computing this. So the total number of true positives over the sum of the total number of true positives plus the total number of false positives. This ratio here is considered the precision. Okay. Another important way to measure how good our classifier is called the recall, also called sensitivity, and it answers the question: how many of the positive examples were correctly identified as positive? So this means how many of the spams examples were detected by our algorithm. In this case, we can compute it just like the total number of true positives divided by the total number of real positive examples in our data set. So precision and recall are very common measures that are used to compare different algorithms. Depending on the domain of your problem, there are some others that are more useful or important to compare. So this depends a bit on the, as I said, on the domain of the problem. Like the general way to do that is to compute a ROC curve, which is a receiver operating characteristic curve. And in that curve you compare two measures, which is the true positive rates versus the false positive rate. The true positive rate is what we just explained as the recall or sensitivity, and the false positive rate is defined as 1 minus the specificity, where the specificity is the total number of true negatives over the false positives and the true negatives. And this is by far like the most common way to compare or to measure how good our classifier is. The true positive rates is simply how many of the positive examples were detected. So if your algorithm detects every single spam in your email, then you will have your classifier will have a score of 1 because it because it detected all of the spam emails. And if your algorithm detects all of your non-spam emails, then you will have a 1 in the as a score for detecting all the false positive examples. So this curve is generated by changing the threshold of your classifier. Every algorithm can be, let's say, tuned by changing a threshold that will depend on the kind of algorithm you are going to use. And when you increase or you move the threshold, sometimes, for example, if you want to improve your classifier so it will increase the number of true positives, maybe when you increase the number of true positives detected, you will also increase the number of false positives, which is not very good. But you can generate with different values of your threshold different behaviors, different trade-offs between true positives and false positives. So this curve is considered to be a probability of what is the probability of detecting a true positive given your current model. And the area under this curve is called the AOC, or the area under the curve, the ROC curve. And this is a measurement of how good your algorithm is. So if you have a model which a larger area it means that it's a better algorithm. So if you have an algorithm which ROC curve is something like this is simply a very bad algorithm, because it says that it is the same probability of selecting a true positive or a false positive. In the other extreme, if you have a curve that goes exactly up here and then here, that would be like the optimal classifier, because at any point you will have always perfect detection of the drop positives. So normally you will have curves in this up side of the red line. Okay.